Okay, good afternoon. Let us start a new subject today, which is time-dependent perturbation theory. Okay, just to distinguish from what we have done so far. So far, we posed the following problem. We have some Hamiltonian we know how to solve. We included some time-independent perturbation, and we want to know what are the new perturbed states and the new energies, okay? And we expanded both these quantities in powers of V. Up to second order most. Okay, now we do a different problem. We have a similar problem, H0 we know how to solve, but now we include a perturbation that depends on time. As a consequence, the full Hamiltonian depends on time. There is no point in trying to do this, okay? Whenever the Hamiltonian is time dependent, you don't search for eigenvectors and eigenvalues. What you try to do is to solve the following problem. You apply this to a state, and you set this equal to I h bar, the derivative of the state. Okay? In other words, you write the Schrödinger equation in its time-dependent form. Okay? This is always true, even if the Hamiltonian is time-dependent. Okay, so we try to find now expressions for this state which are perturbative in some sense. Okay? We'll see how. Is this clear? Indeed, we will see that the formal machinery is almost easier than what we did there. Because there, you remember, we had to write a power expansion for this and for that. And the two sides were kind of a bit unsymmetrical, because V here is appearing up to first order, while in all those terms, there were all powers of V. By the way, to distinguish the different powers, in some of the formulas, we used a lambda close to V, which in principle you could put to 1 in the final calculation. And in order to do the same, to work with the same spirit, we also put a lambda here, which will show up clearly the different orders. Okay? So this, you will see, is even more symmetrical, easier in some sense. Okay. Now, whenever you tackle this problem, first of all, you want to make use of the fact that H0 is something you know. Well, if it is something you know, it means that you have solved, for instance, this problem. Okay? Once again, let me be very schematic. N is some label. Might be several integers, continuum, whatever. I know the eigenfunctions Phi and the eigenvalues En of H0. Certainly, this is information I must try to use. I do not expand the state on arbitrary objects. It's better if I start expanding over those objects, right? So, for instance, if this was not there, so if Phi was not there, how would I write the state of the time-dependent problem? I would write it like this: sum over n, some coefficient, Cn, then I would have e to the minus En times t over h bar, then I would have Phi n, right? So I write the state at time t equals 0. I write it as a superposition of certain of the state Phi n, okay, with Cn being simply given by the scalar product between Phi n and the state at time 0. and then I know that the solution must be of this form. In other words, the Cn simply gets a factor that is e to the minus En times t divided by h bar. Is this clear? Okay? So if I know how to solve the problem, I know how to solve the time-dependent problem because I just need to, say, expand the initial state on the basis, and then the solution is simply that. Now, what happens if I have this PCN? Well, I can try to make use of that and say that I expand still on the same state. I again include this evolution. This evolution somehow takes care of this piece. However, I must assume that the coefficients now depend on time. Okay? You realize that this is still a very general way of writing. Okay? I have a fixed base. I include some phase factor, which will be useful. In a second, you will notice why this is useful. Okay? I might start with this. This is a good way of starting. This is a basis. I expand with certain coefficients that depend on time on the basis. Okay? And I try to find the equations for Cn of t. But for a reason that you will immediately understand, this is better. Okay? So I extract from those Cn a phase factor that is the free evolution of H0 with the unperturbed phases. All right? Let's see. Let's see what equations the Cn have to obey in order for this to be a solution of this problem. Is this clear to everybody? The setting of the problem. Okay? So I plug this there, and I equate to that. Okay? So let's see. I, h bar, the derivative with respect to time of the sum over n of Cnt e to the minus I Ent over h bar phi n. This is fixed in time. How much is this? Well, the derivative acts in two places, 1 and 2. Okay? Let me first write it in 1, and I have I h bar sum over n, the derivative of Cn, okay, times the same phase, plus a second piece that is I h bar sum over n, Cn. Now, when I take the derivative of the exponential, I get down minus I En over h bar, and then I have the same exponential again. Okay? Is this clear? Very easy algebra. All right? Now, let me look at the right-hand side. The right-hand side is h0 plus lambda v applied to this very same thing. So to sum over n of Cn phi n. Okay? Now, h0, when you apply to this is a linear sum combination, and everything is here linear. H0 is a linear operator, and therefore this is equal to the sum over n of Cn h0 applied to phi n. Okay? Plus lambda v, well, let me write it as plus sum over n Cn lambda v applied to phi n. Okay? Yeah. It is missing. Let me put it here. Whatever, I can put it. Let me put it here. Okay. Thanks. Yeah, this was evidently missing. Okay. Now, the first piece is very simple. H0 phi n is simply equal to, so let me rewrite this. This is equal to sum over n, Cn. This is a Cn of t, obviously, but I'm shortening it. Okay? Cn of t. Then I have En. Then I have e to the minus En t over h bar. And then I have phi n. Okay? And if you notice, check this term against this. You see, I and minus I gives me a plus. So this is really a plus 1. And h bar goes away with the other h bar. So this is exactly the same thing. Okay? So you see, by putting this phase factor, which I know is the free evolution in the unperturbed case, I somehow cancel two terms. I cancel, for instance, the term with h0 on the right-hand side with the term coming from the derivative of the phase in the first. Okay? So it's useful. Not essential, but useful. All right? Very good. Once you do that, you realize that the only two terms surviving are this and this. Okay? So let me write it again. I have I, h bar, the sum over n of the derivative of Cn with respect to t times e to the minus I En t over h bar times phi n has to be equal to the sum over n, still of Cn, well, of t, e to the minus En t over h bar, lambda v of t applied to phi n. Now, these are sum over n, but they are, I mean, just dummy labels. I might call this sum over n, sum over m, whatever. Now, what this equation tells you is still an equation that is a bit, I mean, sum over many vectors. I would like to have an explicit expression for the Cn. What do? There's a standard trick to do that. Whenever you have a sum over n of certain states, what you do is you take the scalar product with the basis is orthonormal with a given object, okay? For instance, let me call this the sum over m, okay? I take the scalar product with phi n. This will take out of the sum only one contribution surviving, the one where m is equal to n, okay? So by doing this, I am able here to extract I. No, the unperturbed Hamiltonian I am assuming is time independent.
Okay, then y of n, they are time dependent, meaning how can it be then Cn like function of t?
They are not function of t. Phi n are not function of t.
Then Cn is the projection of y onto psi 0. Those are time dependent, so why we wrote Cn as a function of
No, I'm sorry. This was what I told you is if you want to express any initial state, psi 0, in terms of this basis, then you calculate the Cn in this way. But these are the Cn at time 0. Then how do they evolve? It's something that is in principle non-trivial. Okay? Why in this case, the evolution is simple. Once you have the value at time t equals 0, the value at any t is just this. Now it's not the case, okay? So I must really account for the time dependence explicitly, okay? If this argument confuses you, let's do the following. Just forget about this line here, okay? Okay? So forget about that. In principle, I can write any state, where did I write? In this way, okay? Because this is certainly a legitimate way of expanding any state at time t in terms of a fixed basis, phi n, fixed, with certain coefficient, which, for a reason that I like, okay, and I don't tell you, I write as Cn of t times this thing, okay? Now, due to this very bizarre choice of me, two terms cancel. Okay, so this is the actual thing. So the phi n do not depend on t, the h0 does not depend on t, and this is a choice that would be somehow the right one if there was not this, okay? Without this, you would get this and no time dependence there. But with the thing, I leave that because I like it, but I put the time dependence here. Okay? All right. Now, so taking the scalar product on the left by phi n, here I get I h bar, the derivative of Cn in dt, e to the minus I e n t over h bar, and nothing else. Okay? So I was able to just pick up only one term on the left. On the right, let's keep writing this as m. I will have the sum over m of Cm of t e to the minus I e m t over h bar. And then I will have phi n lambda v phi m. Notice that on the left, there was only the state, and therefore I could use the delta, orthogonality. On the right, there is also another operator, so I'm not entitled to use any delta. There is, in general, this object. Okay? So if there was no thing, I would use the delta. But unfortunately, there is the lambda v, and I have to write it this way. So the right-hand side is a sum. The left-hand side is a single term. And indeed, you realize that you can bring this guy together with his friends there. Okay? So I just multiply by e to the plus I omega t. Okay? And if you allow me, I will do that here. Okay? You see, I have Em minus En, the difference in energy between these two guys. All right. Actually, let me write it opposite. So I write n minus m with the plus. Okay? So that I have the same n, m, n. Okay? Good. That's it. This is our equation. This is still exact. No perturbation theory yet. Okay? It is the exact expression that all these functions, Cn of t, have to verify in order for my expansion here to satisfy the Schrödinger equation. Okay? So you realize this is a big thing. Not easy to solve at all. Indeed, you see, it's a system, an infinite number of differential equations, okay, linear, in the Cn, but coupled, and therefore quite a complicated thing. All right? Good. Okay, now, so all this is general and exact. Let us try to solve in an approximate way. Let me erase here this. I erase this.
Sir?
Yeah.
Here, okay, we choose C to be like function of t, right?
Mm-hmm.
Why not, why not be like a function of position or space, just...
Oh, position and space, everything is in the states. You see, I'm using an abstract notation here.
Yeah,
Ket.
yeah.
Not wave function. By the way, this would be more general in principle, what I write. So it would be for, if I had a spin system, there would be no position, but still the cats and things would obey this thing. If I have more than one particle, then I would have several positions. So in some sense, the initial choice that we make from the beginning of writing psi of x is a very peculiar choice. I mean, it forces you to continue working in position space, for instance. But sometimes it's useful to change and analyzing things in momentum space, for instance, by working with Fourier transform of wave function, and so on and so forth. I would say that now that we have, we are grown up, we use the abstract Ket notation in a more confident way. We know what they mean. I mean, if I have a single particle, blah, 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 then by taking this, okay, I would have psi of x and t. And obviously here I would have phi n of x. Okay? We know exactly how to reproduce any wave function. So the x, if needed, is hidden here and there. Okay? These functions are just functions of time. That's it. Okay?
Yeah.
Not space.
Yeah, because the differential is not exact, right? When we change it into d by dt, just when we reach here, it was originally just the partial of Cn.
Well, it is a partial thing here, but in some sense, because I assume that inside this belly here, there would be also position. By the way, when I write for a formal ket, I might even use the total, the derivative, because in some sense, t is the only variable there. Okay? Then, when I write this way, there is also x. And therefore, I mean, to remind me of that, I keep using the derivative, partial derivative with respect to time. But there is no ambiguity whatsoever in Cn. Cn has only t. So there is no need to continue and insisting in writing the partial derivative. Okay? That's the reason why I write total derivative.
But I still have doubt on Cn.
Huh?
I still have doubt on Cn. We just choose Cn to be like a function of t. Okay. I don't know, but it has some property, I mean, some meaning later. I don't know, in Cn maybe. And then if we
I will tell you immediately the meaning of it, but if you don't like this, I might write the first thing like this. Now, is it true that for any, even in higher dimension, I can, if I have a basis function like that, I can always expand this thing as sum over n, some coefficient of t times the basis function for any fixed t. So you realize that x appears there, appears in the basis function, but not in the coefficient. Okay? For every t, I do reconstruct all the space dependence with a set of just coefficients, some numbers, no x there. Okay? Does this that this clarifies to you? Okay. So the only thing that I put more there is that I like to put an extra phase because this is useful. It cancels a piece. And the other thing I did is that I didn't write this as x psi of t and x phi o n, but just kept this and that. Okay? So that's the full derivation of that equality. So you shouldn't worry. C are just time-dependent coefficients. Okay? Cn. Infinite, however, not just a single. Okay, so no x appears there. And in this way, by the way, it applies to spin systems in which there is no position. Okay, now, you might say, ask, what is Cn? Well, obviously, Cn must be related to, for instance, the probability of finding the system in a certain eigenstate at a certain time, for instance. I'll see in a second, so let me not anticipate too much. Okay? Good. Before we point this, let me just tell you what I should do to do now a perturbative expansion. I take this, and I assume the following. I say, okay, Cn of t will be some unperturbed object plus a term first order in lambda times C1 plus a term second order in lambda times C2, okay, plus, you understand, right? Now you see that I have only one thing to expand, the Cn. Before I had phi and e, and I had to match the orders. Now you will see everything is much more straightforward, okay? So I use that expansion there. And I notice that here there is one more lambda because of the v on the right-hand side, okay? So on the left I have I, h bar, then I have the derivative of C0 with respect to time, plus lambda, the derivative of C1 with respect to time. Well, I should put the n, really, everywhere. Plus lambda squared, the derivative of C2 with respect to time. Plus dots equal to, right-hand side, sum over m of, let me use, well, later, okay. I will soon propose a shorthand for these energy differences and for these matrix elements, okay? But for the time being, let me write it fully, okay? So here I have C0m plus lambda C1m plus lambda square C2m plus dots, okay? There is a t obviously here, but, well, let me write it. Okay? Times, yep. Well, let me finish the times e to the I, En minus Emt over h bar, times phi n lambda v phi m. Yes, question?
The way we introduced our Cn of t, it looked as if it is not dependent on h naught.
No, I don't understand the question. Can you repeat?
At least on the way we wrote in our Cn of t, I thought it is not, okay, it is much more linked to h naught, not the potential that we are introducing. But then when you include lambda, the same constant, it was there.
I don't know if I understood the question. I try to repeat. You thought that this... No, I don't really understand the question. First of all, let me stress that these are time-dependent functions, okay? So let me try to explain, then maybe you reformulate the question. Okay. At this level, okay, I hope it's clear what the Cn of t are. Now I try to say the following thing. I want to obtain, in a recursive way, a power expansion of Cn of t, a power in lambda. So as any power expansion, I write a zero order term, first order, second order, and so on. Is this clear? So the 0 here means zero order in lambda. 1 means first order in lambda, 2 means second order in lambda, and so on. Now, if I use that, I realize that I do have a recursion, because on the left-hand side there is no lambda, on the right-hand side there is an extra lambda. Okay? So I'll see in a second that whatever is on the, I mean, the matching of the lambda now, for instance, let's see. To order lambda to the power 0, I have this. But here, there is at least one lambda, okay? So the equation for this object here is I derivative should be equal to 0, okay? Is this clear to everybody? Now, maybe you want to make the question again?
My concern was, we introduced lambda came in with the perturbation.
Here.
Yes. Yet the general solution, which includes the constant Cn, is normally for h naught. Before you gave it the time dependence.
No, I feel I still don't grasp. I mean, these are unknown functions. I don't know what they are when there is this object, okay? If there was no v, then I know that the behavior of this function as a function of time would be very, very simple. A constant times a phase. But once I have that, I don't know this function, okay? So it's not that I know it in some, I simply don't know. It's a function that I have to calculate, all right? And I'm trying to write the differential equation for this function and trying to propose a power law expansion. So I don't know if this, the spirit of this is clear enough. This function is unknown. It's not that I know it in some limit because h0 is, no. Cn of t. I don't know it, okay? So I reduce all my uncertainty on the state, on what the state is, rather than on the state, on some unknown function C n of t, the components on the basis vectors. Okay? Any vector can be written as on a given basis. Now, the vectors depend on t, and therefore the components on the state vectors depend on t. So these are the components of the vector. If I have a particle moving in three-dimensional space, I can write the position as x, y, and z component. The particle moves, the x, the y, and the z component move. Okay? Same thing here. I simply wrote the components of the vector psi of t on the fixed basis. And I have to find this. Okay? So until here, it's a very simple thing. Just the components have to respect this differential equation because Schrödinger imposes it. All right? Now comes the business. Now I have to learn how to solve it, at least in some approximate way. Okay? And to do that, I use the fact that there is one extra lambda, one extra v on the right than on the left. Okay? So I realize that if I write, I don't know if this is clear, because otherwise there is no need to continue. Is this clear? Okay? So these functions, which I don't know, I write as a certain function which wouldn't depend on lambda. Okay? Another function which is times lambda. Another function times lambda square. And I pretend that order by order in lambda, this thing, when I put it on the left, equates the right-hand side. Okay? This is now a requirement for all this C0, C1, C2. Okay? It looks like it's, it's proliferating the number of objects that I have to find. But it's not so in the end, because I will see that, for instance, C0 is trivial. Okay? C0, it appears on the left-hand side with the derivative, but on the right-hand side, there is at least one lambda. Okay? So on the right-hand side, I must put 0. Is this clear to everybody? Why I write this thing equal to 0? Because I want the same order on both sides. On the left-hand side, I have order 0. On the right-hand side, no order 0, so 0. Okay? So let us write the equation for first order. First order means a single lambda. On the left-hand side, I have I, derivative of C1, n, equal. Let's see what I have on the right-hand side, first order in lambda. You would be tempted to say this. No, this is not first order in lambda, because this is already first order. So I have to take this times C0. So I have sum over m of this coefficient here, e to the minus I, en minus em t over h bar, phi n, lambda v. Well, I can take off the lambda at this point, okay? Just v of t, phi m times C0. Okay? Is it clear to everybody? Huh? H bar. H bar. Okay? So you see, the first one is simple. Indeed, it tells me just that Cn of 0 do not depend on time. Okay? The second tells me that the C1 derivatives are related to the C0. Okay? The one I just determined. Okay? So I determined the C0. I put it on the right-hand side, and I can get the C1 by solving this. Okay? And by the way, this doesn't depend on t. So for instance, can I solve this? Yes, because now C1 does not appear on the right. So how do I solve this? I just integrate. Okay? So to solve this, I integrate both sides, and I have I h bar, I integrate from 0 to t, for instance, okay? This will tell me that C1 at time t minus C1 at time 0 will be equal to the sum over m of the integral from 0 to t in the t prime of e to the I e m minus e n t prime over h bar times phi n v t prime phi m times c 0 m, which doesn't depend on t, by the way. Okay? So I know everything on the right-hand side. And I calculate this integral, and I get C1. Okay? So in principle, I could now finish calculating the C1, plug on the right-hand side, and, well, maybe I should just first point out to you that the second-order term, okay, you see I have a second order on the right, so the derivative I h bar, the derivative of C2 n over time equal to sum over m. What is the second order on the right? I must have one order is eaten by this, and therefore I can just have C1. So you see, it's a very similar equation with C1 in place of C0. E to the I e n minus e m t over h bar phi n v of t phi m C1 m. Now in general depending on t, because C1 depends on t in general, C0 not. Okay, so is it clear? This is a very recursive structure. So from C0 I get C1, from C1 I get C2, from C2 I get C3, and so forth. All right? So in this sense, although it seems that I have introduced many things, these many things are easier to calculate than just, okay? It's like a successive approximation. I guess some C0s, for instance, constant, okay? And I find them, okay? Then I put on the right-hand side, and I try to get a better, an extra piece, C1. And I put the C1 on the right, and I try to get a second-order piece, and so forth, all right? In principle, I should proceed and calculate all of them. So still an infinite amount of work to do, but one usually stops at a certain time. For instance, one might stop here to first order. Notice this is first order corrections in the states. Okay, these are the state correcting factors, which is essentially equivalent to our second order type of, we stop to second order for the energies, for the state to first order. Okay, so a similar work would be to stop here. Okay, so let's see what do you practically do in a certain case. For instance, you can ask the following question. Let us do a bit of physical questions and exercises. You can say, okay, suppose that for all times before a certain t0, okay, so I prepare my system such that for all times t, before a certain t0, my system is in a state that is phi, how do I set the thing here? A certain phi I, the initial state, okay? A certain eigenstate of the Hamiltonian, okay? So initially I prepare my system there, okay? At this time, I turn on, so here the Hamiltonian is just H0. At T0, I turn on the perturbation, and the Hamiltonian is H0 plus V of T. Question, how would the state evolve? In particular, for instance, what is the probability? I can ask myself, what is the probability that at a certain time t greater than t0, my system is in a given eigenstate phi n, okay? So I can ask what is the probability that starting from I, the initial one, I will end up in any given n different from I at a later time t. So this would be take the state at time t, which I have calculated by this initial choice, and take the overlap with phi n, and then take the modulus square. Now, what is this? Cn of t squared. The phase doesn't count, you see? So this object here is immediately Cn of t modulus squared. So the meaning of those Cn of t is they are the amplitudes which allow me to calculate probabilities of finding the system in any of the excited eigenstates of the H0 Hamiltonian. I am kind of analyzing everything in terms of H0. So for instance, if this was a hydrogen atom, and I turn on some electric field or some potential, whatever, depending, I could ask you, what is the probability that I have excited the system to such and such level, okay? Okay, so the answer would be calculate this appropriate Cn of t as a function of t and square it, all right? So this is the physical meaning. Now let us do it in practice. For instance, with this choice, I know what the C0 are. The C0n, what they are. They must be independent of t. Remember, they do not depend on t. But how much they are here? Simple, just delta n I. Okay, so 1 for the initial given state as I select, state number 3 or whatever, and the 0 for anything else. All right? Okay, so the initial choice is very, very simple. Then let's put it back into this equation. Oh, but before I continue with this, let me just use some shorthand, which I promised long ago. I will call En minus Em over h bar. This is a frequency, okay? E over h bar is always a frequency. I will call it omega nm. Is the excitation frequency, okay, to jump from m to n, which could be positive or negative, depending if n is bigger than m or vice versa, okay? So this is just a shorthand. Second, yeah. Where? Here? Here? Why do you want the sum? Yeah, but I am asking what is the probability of going from I to a given n. N is fixed. Okay? So here you can put a sum. Sum over m. But then I want simply the component n. So out of the sum, only the term with n equal to m survives. Okay? Psi is a sum in it. Okay? Sum over m. Let me write it like this. But then I project on n, and this leaves me only one piece, Cn. Is the answer clear? Okay. Good. So the other shorthand I want to use is this. You see, I always have the matrix element of V of t between n and m. N to the left and m to the right. I simply write this as VNMT. Okay? This should lead to no confusion at all. Okay? It's simply shortened. Okay. With this shorthand, the equation for C1 would look, I write it here, something like this. I, h bar, the derivative of C1 of n, equal to sum over m, e to the I omega nm t times v n m t times C0 m. Okay? This is just a shorthand for that. And since I know that C0 is now a single delta, even the sum, okay? Sorry, now I better, yeah, C0 of m, if you want, is equal to delta of mi. I is the initial, I stands for initial state, okay? So I substitute now this delta here, and what I get is that this is equal to the sum. The sum really disappears. There is only one term, the term number I. So e to the I omega n I t v n I t, that's it. Okay? So the coefficient to first order of the state number n is simply Vn with the initial state times a phase factor. Okay? Is this clear? But it's simply the previous thing. Just a simplification because this is just the delta. I assume that I was in the initial state up to here and then I change. Okay, so the solution of this is simply similar to this except that there is no sum. And the solution is that, so at time t0, in particular, C1 of t0 was 0, okay? So here, C1 of all n for time t less or equal to t0 was just 0. You realize, right? If the solution was just with the C0, all the C1, C2, C3 were just 0 here. Good. And therefore, the solution at time t0, which you see there, is just 0. So let me write the expression. Solution of this is that C1 for state number n at time t would be equal to 1 over I h bar, coming from this I h bar in front. Then I have the integral from t0 to t in the t prime of here. Here I wrote it wrong. You see, it was n minus m. So it's still the same thing. So e to the I omega n I t prime v n I t prime. That's it. Okay? Because the Cn I have taken care of. Is this clear to everybody? T0 to t. So in general, I call T0 the time at which I turn on the perturbation. I could take this to be 0, and then would be from 0 to t. Maybe this is a better thing. Okay. So what is the probability now? The probability is the modulus square of this. Okay. So the probability that at time t, I am in a certain eigenstate n. If I know that I started from I, so I write this as I to n, then this would be equal to, in general, to Cn modulus square. In first order perturbation theory, would be Cn1 t modulus square. Okay? If I go to second order, I should sum C1 and C2. And then I have to square. First I sum the amplitudes, then I square, obviously. I don't sum the squares. Okay? I have to sum the amplitudes and then I square. All right. So is it in principle clear what to do? Okay? The Cn are just obtained in a recursive way. For instance, up to first order, I would need to stop here, and then I have to take the square. If I need to go to second order, I have to put the C1, the solution I get from here, inside this equation, integrate once more to obtain C2, and then write Cn as C1 plus C2, and take the square. Okay? We'll not do that. We'll just stop at first order. Okay? So life is very, very simple for us. all formulas are essentially reduced to something like this. Okay? All right. Let us apply it to, well, do a little calculation. For instance, well, you realize one thing. This thing is like taking some function of time and multiplying by a phase factor. Okay? So if this is a generic function of time, this is like taking the Fourier transform. But if this function of time has a frequency in it, which is exactly this, maybe with a minus sign, then this phase dependence cancels exactly, and this becomes a constant. And therefore, this increases linearly in time. Okay? So this is the most convenient thing for growing of probabilities, when the phase is really compensating into the two terms. Okay? So in any case, we'll see this later on. Just make sure you have an eye for that. Okay, so first problem. I do exactly what I was telling you before, but now, in detail, I want to do this. I turn on, so my V of t, or lambda V of t, is, so H0 is our beloved harmonic oscillator, okay? So do I need to rewrite it? Equal to, you can, for instance, H bar omega, A dagger A plus 1/2, written in the usual A and A dagger. And V of t is the turning on of an electric field. We already did that, okay? Remember, we did an electric field, say Q electric field times X, okay? We did this. However, in this case, I want a time-dependent case. Therefore, I just put e to the minus t squared over some tau square. What does it mean? It means that there is a certain time scale tau over which I turn on the field, okay, which reaches its maximum value, E, at time t equals 0, okay? And then the field is turned on a certain scale tau, and then switched off again, okay? So I have a Gaussian turning on and then switching off of the field, okay? I ask you, okay, given that at minus infinity, so long in the past, the state was in a certain, say, initial state of the harmonic oscillator, what is the probability, for instance, in the ground state? So at the beginning, I was in ground state, I equal to 0. This for time t0 equal to minus infinity, okay? Then I turn on the field like that, and I switch it off. And I ask you, what is the probability that I went from 0 to any excited state n when I have now for very large times, okay? So here, there is again no electric field, but I have switched on and off. And I ask you, what happened to the poor harmonic oscillator? It's still in the ground state, or it's in some excited state? And if so, with which probability it is there? All right? So this is our first simple exercise. This can be done essentially exactly in first order perturbation theory, by the way. Because this calculation is very, very simple. So I have to calculate this from minus infinity to t, for instance. And indeed, I then want to simply t equal to infinity also. I could ask you what is the probability of being at a certain time in a certain state n, but I am generous and I ask you to calculate simply the t equal to infinity value. Otherwise, the integral you will get is a Gaussian which wouldn't integrate, okay? But for t equal to infinity, this is what you need. What is this? This is the matrix. Well, I need the initial state is 0, the ground state. So what I need to calculate is right here. V n0 t prime is this object calculated between the state phi n and the state phi 0, the initial one. So I have to calculate this. Between these two states, okay? And then I have to integrate I have to multiply by this object here, okay? Okay, so what is this result? It's very simple. This is Q, the charge of the harmonic oscillator, A, the electric field, and then this is L, and then I have essentially A plus A dagger. So the time, really, I can take it out. Okay, then I have phi n, A plus A dagger, square root of 2. Okay? A very, very simple thing. Now, A gives me no contribution. A dagger, however, gives me contribution where the only possible n that I can reach is 1. Okay? So to first order in perturbation theory, turning on and off an electric field can only change me from the ground state to the first excited state. That's the only one that has a matrix element directly to that state. I cannot go in first order perturbation theory to the second, to the third, and so on. Okay? Those states, I will only be able to reach them in higher order perturbation theory, and therefore, obviously, with smaller probability. All right? Okay, so to this order, I do have simply here Q, E, L, the harmonic oscillator length divided by square root of 2. Then I have e to the minus t prime square over t tau square, and then I have a delta of n1. Okay? Good. So let us calculate here the result. I have 1 over I h bar. Then I have integral from minus infinity to plus infinity in dt prime. This is n and 0, but I really only need n equal 1. Omega 1, 0. Omega 1, 0 means E1 minus E0 over h bar. How much is this? Huh? Well, no, the half cancels. The half cancels. It's just omega minus 0. So it's just omega. Okay? So this is just omega. So I have e to the I omega t prime times, well, times, I have a delta of n and 1. I have q epsilon L over square root of 2 and e to the minus t prime square over tau square. So this is just a constant that I can put out of the integral. The only thing that I have to integrate is this Gaussian term, okay, Fourier transform. Now, this is the reason why I ask you to do to plus infinity. Otherwise, I would have a Gaussian integral that I would know how to calculate. But this integral is very, very simple. And you know that the result, so we did it probably our very first lecture. The integral in dt of e to the minus t square over tau square e to the I omega t is equal to the square root of pi tau square e to the minus omega square tau square over 4. Okay? The important thing is that the tau from the denominator goes into numerator. Okay? Remember, Fourier transform of a Gaussian is a Gaussian, but with inverted widths. Okay, so if you go and look at our formula in the first lecture, that would be the result. Okay, so this is it. Now I have to take the modulus square of this object. Okay, and I conclude that this probability is equal to, well, delta of n1. Only one can be excited. Here I have 1 over h bar square. And here I have q epsilon L square over 2. And then I have the square of that integral. So I have essentially pi tau square e to the minus omega square tau square over 2. Okay? This is it. L square, well, you know, right? L square is there are m's and omegas appearing here, and h bar, by the way. You can erase this, okay? If you want, you can. This should be. Wait a second. I missed something with respect to the formula. Oh no. Okay, L square has an omega in it. Okay, remind me. L square is equal to over m omega, right? Okay, so once I divide by, so this is h bar over m omega, and one of the h bar goes, and the other gives me h bar omega. Okay? So this is the result. Some electric field square, charge square, m, the energy of the oscillator, some pi's and 2's, and then the crucial object that is this tau square e to the minus omega square tau square over 2. So this probability is very, very small in 2 limits. If I do, remember, tau is the time over which I turn on the Gaussian. Okay? Well, if tau is very small, which means I do a very quick switching on and off, then this goes to 0 because this is close to 1, but this has a tau square. But if tau is very large, so it means I do a very adiabatic turning on and off. So this is tau large, and this is tau small. Then also I have a small probability, because now what makes the result small is this exponential. All right? So this probability of excitation is small, both if I do it very fast and extremely slow. In the middle, it's larger. All right? So this is a simple example where you can calculate some probability of exciting some particle when you devise some electric field. You ramp it up, you ramp it down, some experiment, and you ask what is the probability that I have excited my system. That's the result. All right? So it shows you that you can do also more physical problems in which the fields change in time and things like this, because, I mean, things are not always constant in time. Okay, so I hope this was a very simple illustration of the typical calculation that you have to do in this business. Now, before we go away, let me do for you another simple exercise, which shows you how to get the result we got last time for the first order correction to the states in this new business. Okay? We'll see we will get exactly the same formula. But now the device we have in mind is the following. Suppose that I have a system that I have prepared at minus infinity in some state, and then I add a time-dependent perturbation, v of t, which is the following, is e to the t over tau times some fixed perturbation. Okay? It means that for very negative time, this is very, very small. This is called adiabatic switching on. So I switch it on very slowly in a time scale tau, and then it reaches its full value v only at time 0. Okay? And then stays constant. Okay? So from t positive, from 0 on, the perturbation is fixed in time, is v. But in the infinite past, it was starting from 0 and it was switched on adiabatically. Okay? So adiabatic switching on. Okay? Is the problem clear? So at the beginning, infinite past, no perturbation. Then a slow exponential increase of this perturbation up to a value at times t equals 0, which is v, and then constant. I ask you, what is the state at any time t? In other words, I want to know the coefficient, Cn of t, later on. Obviously, I want to stop at first order, okay? No second order, okay? The solution is very, very simple. So, let's see. Oh, by the way, initial condition is that at t equal to minus infinity, the state was n. Okay? I was in a given eigenstate n, so if you want C 0 of m, it was just the delta of n m. Rather than using I prefer to use the value n here, for a reason that you will understand in a second. Okay? So this is my initial condition. Okay, so let us calculate the result. Well, it's the same approach, obviously. But now the ingredient that I need, let me erase a few things. Let's see. For instance, I might ask you, what is the probability, what is the state at time 0? Okay? So the time that I really want is 0. Because at this time, the perturbation is fully settled, right? So I want to know there what happens to the state. See, if I started at very negative times from a given phi n. Then, essentially what you want is the following. You want to calculate the state at time t. Let's see, how do I put it so that I do not confuse you? Okay, so I would have C0 would give me the phi n. Okay? By the way, last time when we did time-independent perturbation theory, we added an extra 0 here. Since we were perturbing the state as well, we wanted to know which ones were the ones for H0 and which ones they were the corrections and so on. Okay? So to be consistent with that notation, I should here add H0. Okay? So I start from very negative times from the eigenstates phi n of H0, unperturbed. Then I switch on the perturbation and I ask you at time t equals 0, what do I get? So obviously, I do have the usual thing. So at time t equals 0, I would have the sum over all n of Cn of t e to the minus I E n t over h bar phi n, where this phi n now are the basis of phi 0. I reintroduce the index 0 there. At time t equals 0, I have to put here a 0, and I have to put here a 0, and so forth. That is not important. So all I need to know is this object at time t equals 0. Now this object is a C0 plus C1 plus other things. And I want to stop just at first order. Okay? So I just keep those two. Okay? So the first piece is simply, since the C0n is a delta, I do have here, let me write it as sum over m. Okay? This is simply the delta of n and m. And this first term will give me phi0 of n, the initial state I start from. Okay? Then I have the second piece, which will give me sum over m of C1m of 0 times phi 0 m. Okay? So this is the result that I need. By the way, this is only phi m for m different from 0. Okay? Now let me calculate the C1 from this expression here. I write it here. So I have that C1, rather than n, I call it m, at time t equals 0 would be equal to 1 over I h bar, the integral from minus infinity to plus to 0, because I want at time 0, in dt prime of e to the I omega, I want to end up in n m starting from n, then I have a t or a t prime, and then I have the matrix element of the perturbation. So I have the matrix element of phi n, sorry, tm. Then I have the lambda, the v, okay, the v, the phi 0 n, and the v has a time dependence that I assume to be simply e to the tau t over tau. Okay? Is this clear? I just copied all the ingredients in the formula and I adapted it to this time dependence. Now, this integral here can be done now. You see, it's an integral of an exponential with an imaginary piece and the real part. Okay? So you know how to integrate exponentials, and the result is simply, what is it? Tell me the result. 1 over I h bar is there. The result of this integral, let's see, it's e to the primitive is e to the I omega n m n plus 1 over tau times t prime divided by the same thing. Okay? And all this has to be evaluated between 0 and minus infinity. And then it has to be multiplied by phi 0 m v phi 0 n. Okay? Now, in 0, this is 1 divided by this thing. And in minus infinity, due to the fact that there is a 1 over tau, the minus infinity is just 0. Okay? So no need to take the minus infinity, just 0. So, okay, so all this becomes just a 1. So 1 over I h bar, 1 divided by I omega m n plus 1 over tau times the matrix element there. Now, suppose this is to first order exact. Suppose that tau is now very, very, very large. It means that I turn on this thing very, very, very slowly, okay? Large tau means, I start doing a very, very, very soft increase. Then if tau is very large, 1 over tau is very small. Drop it. Now, I and I is just a -1, and h bar times that is simply En minus Em. So I rewrite this probably up here, and this would read 1 over E unperturbed. These are unperturbed energies. N minus Em times the matrix element V 0M V phi 0N. Okay? So this is obviously summed, should be summed over all M different from 0, from N, from the initial one. Okay? So the result is that the state has a piece, so I should put this here, a piece like sum over M different from N, this thing times phi 0M. Okay? Now, I probably messed up a little bit with the N and the M. Probably not. No. It's perfect. It's incredibly right. Okay? So this is the result of my calculation. There is a first piece, the state at time t equals 0, if you slowly switch on the perturbation, will be the original one, the N, plus a correction, which is nothing but what we calculated last time in first order perturbation theory. Okay? So the perturbation will act in first order in exactly the same way, in some sense. Perhaps it's not surprising. But in this way, we got the result by a time-dependent calculation, which is adiabatic switching on a perturbation. Last time, we did it algebraically in some multiplying, take the overlap, and things like this. Okay? So this is somehow instructive. First order perturbation theory is first order in all possible settings. And you can reach the same result even by working out an adiabatic switching on of the perturbation in this way. Okay? Which I think is pretty instructive. You see, the state is modified by acquiring components on all the other states with matrix elements that are the matrix element of the perturbation divided by the corresponding energy differences. Okay? So this is the end of this lecture. Next time, we do the important case of a perturbation which is neither switched on and off, but is oscillating forever, like the cos of some frequency times t. Then we will see that this immediately selects some resonances. So the states that are mostly sensitive to this are the ones for which the frequency exactly matches the energy differences. Okay? This is the idea behind exciting an atom with a laser. You select a laser frequency which exactly matches the difference between two levels, and that transition will occur essentially with certainty. Okay? You say on resonance. And this is very, very important, obviously, in physics. Nuclear magnetic resonance, the same thing. You put your system into a uniform field, and then you put a transverse microwave field whose frequency matches exactly the Zeeman splitting between these two spin levels. Then the spin will do zoop, flip, like that. And obviously, then it would flip back and it would do like that. But important thing is that there is a large probability of exciting this thing, and therefore getting the field absorbed. And this is measurable, and this gives you information on this energy. All right? So all these phenomena are resonance phenomena that are behind behind this formula, okay? Just behind that, there is a resonance object that we'll discuss next time. Questions until now? Well, I mean, it's probably easier if you try to do the, I mean, if I change it several times from n to m, this might be a source of confusion, okay? So if you try to do the following problem, you start at a given infinite past in some eigenstate n of the Hamiltonian, and you want to calculate what is the state at time t equals 0 when you have turned on the perturbation to first order. Then you have the very same state for sure, because after all C0, which doesn't change of time in time, will persist forever, and therefore that state will be still there. But on top of that, you will have a piece coming from C1 M. C1 involves matrix element of the potential with all possible states. And therefore, when you integrate, will give you quite the right coefficients, which we got last time by the first order perturbation theory. Perfectly compatible, perfectly the same, as it should, obviously. Okay? It's the same type of calculation, done in two different ways. Okay, so next time we do the periodic thing, and we do Fermi golden rule, and that's it. Okay?